Now, what then Sharpless did was that, as I told you, Sharpless was obviously found his allyl alcohol very restrictive, and he wanted to generalize it to olefins much more broadly, you know, and so he didn't want to only work on allyl alcohol. Okay, now. Have all of you, are you aware of the reaction of olefins with osmium tetroxide? Anyone? Okay, probably no. It was known since 1935-36 that osmium tetroxide is a very good reagent for converting even simple olefins into a dihydroxy compound. And so that's very powerful because now you've got two functional groups which you have introduced into the double bond, and then you can actually use those for making all kinds of compounds. And so it's one of the very powerful approaches that people take to make more complex molecules out of simple molecules. Okay, I mean, that's what it is. Now, this person who actually discovered this reaction, his name was Creigee, and he discovered that around around 1936. But then Creigee also said something very interesting, and just like we saw the ligand acceleration effect, which Sharpless had found with tartaric acid, that when he took this Creigee, when he took pyridine, okay, along with the osmium tetroxide, okay, that it really accelerated the rate of the dihydroxylation reaction. So that was something that Sharpless was aware of. Now, this is another thing. I found that all of the truly great scientists, one thing you can see that do not ignore things which have been done in the past, because they can actually be a source of inspiration. And I can see that Sharpless drew all his inspiration from very old literature, not this contemporary stuff that people talk about. The second thing was that they've got a way of not only drawing on that information, but then putting it to their advantage by keeping in mind what they specifically are interested in. So, for example, Sharpless, because of his interest in asymmetric synthesis, he realized that, look, if I take an olefin, okay, where when I introduce two hydroxyl groups, and suppose my olefin is such that it's a prochiral olefin, that is, once I make the hydroxyl groups, the compound becomes optically active, and there are two chiral centers. So, and his interest was chirality, his interest was asymmetric synthesis. So, just like Knowles had thought that why can't he make the Wilkinson catalyst chiral? And how did he do that? He did that by really making the phosphine ligands chiral. Okay, that's what was the approach that Knowles took. And so, similarly, Sharpless came up with a brilliant idea, and he said that, look, of course, Creigee has reported pyridine, but it may not be only pyridine. Maybe it is nitrogenous compounds, amine type of compounds, which can accelerate the rate of the reaction. And can I go looking for some chiral amines, which might actually give the acceleration? And who knows, if I'm lucky, like in the case of tartaric acid, maybe I will also induce chirality. So I hope you can see the manner of their thought process. Okay, well, it's quite nice. And now, of course, with hindsight, many of these things look obvious, but actually, frankly, they're not obvious at the time that one is conceiving the idea. Just very similar to even if you look at Arthur Eddington, to draw on the old literature that there is a mass to energy conversion, and helium has a slightly lower mass than four hydrogens, and then to put it together and say that maybe this is how the what is happening in the sun, that there is nuclear fusion. I mean, that actually requires a totally different kind of ability to synthesize very, very creative concepts out of information that exists. But putting it together is not so trivial, you know. And if I get time, you know, I'll take you through more of these examples. Okay. Now, so what he did was that I've already told you that nitrogenous compound, like if you take a simple tertiary amine, that you cannot make it chiral simply because of the umbrella flip-flop effect. Okay, but all that changes. Okay, if, for example, suppose I tie up the nitrogen in a way that, for example, you take these bicyclic compounds. You know, this is also an amine. It's got three bonds around the nitrogen. Okay, and there is a chirality which some of these things have at some point. But these ones will not flip flop like that. Okay, and we already talked about the work of Bredig, you know, where he had used the cinchona alkaloid long time ago in 1912 to make some of the fused organic compound, and that was the birth of really asymmetric synthesis with in a synthetic manner, not making use of enzymes, but making use of organic, simple organic molecules which you can get from nature, like the alkaloids, okay, like these. Okay, so when he did this reaction with this chiral alkaloids, okay, he was able to actually then make the chiral form of the dihydroxy compounds, okay, from here. And there is an osmium tetroxide is the oxidizing agent. Okay, and this is a stoichiometric reaction, this particular thing. So the osmium OSO4 is osmium 8, and after the reaction it becomes osmium 6. So osmium gets reduced and these get oxidized, and so that's where the oxidizing equivalent comes from. And this amine was actually bestowing the chirality. Okay, and on top of that, you know, he would have probably got a ligand acceleration effect that could have happened. Also, what is very interesting is that when Sharpless did his work, uh, he did not actually do it with the simple alkaloids, the cinchona alkaloids. What he did was he made a dimer of of these. Okay, so this is one part, and this is the other part. Okay, and now that's quite interesting that he did that, and it. I was just thinking that maybe he drew upon the idea of from the asymmetric hydrogenation work, that after Kagan, everybody started working with bisphosphine, the bidentate ligand. So maybe he thought that something like this could be of interest even in the oxidation process, and so that's why he probably used a linker, you know, and linked up, you know, two of these chiral ligands. Okay, and so that's what he did. I mean, it was really a wonderful idea. But then, as I told you, the cinchona alkaloid is not as if Sharpless used it for the first time, that it had been used as early as 1912. But he applied it to a different set of reactions. That, of course, was the novelty of his work, rather than specifically the cinchona alkaloids. Now, there's something else that made this asymmetric oxidation so attractive to industries. And Sharpless summarizes that quite well. He says asymmetric dihydroxylations are tolerant to air and water and work best at high concentrations. Can you imagine? I mean, it's like the best of both worlds. Uh, and he put equal to suitable for large scale preparations of enantiomerically pure diols. So, how many things, most of us tend to carry out reactions under dilute conditions, thinking that concentrated solutions may give you side products. But that's not what Sharpless found. He actually found that higher concentrations, which obviously means that you can have a much higher throughput from your process, that's what gave actually the best induction, chiral induction. So it was really, in that sense, a win-win proposition. Nothing can be better than that. And look how beautifully he exploited the work of Creigee, a pyridine, then thought of a chiral pyridine, then probably drew inspiration from asymmetric synthesis, hydrogenation, and made a dimeric form of things equivalent to bidentate ligands, and was then able to show that at high concentrations he gets better results. So whichever way he actually won. I mean, and that is what made him such a great man. Okay. No, in fact, I was also trying to see, and I always do, that can I think of some places where we applied or found something similar? Similar means a win-win concept. That's what I mean by similar. All of you would have heard of agarose. Agarose is probably the most important thing in molecular biology, because when you run these do gel electrophoresis, you do it with an agarose, and that's how you separate the bands of DNA and things like that. And so agarose is a vitally important molecule, and all of the good agarose used for molecular biology was really being imported into our country. I mean, we did not really make any agarose, although we used to make agar. Agar is what goes into all your jello pudding and things like that. There's not that much of a difference between the structures. Okay. Now, what happened was that in 2004, around that time, one of my colleagues, for the first time, was able to identify a seaweed in Gujarat waters near Porbandar, and he extracted agarose or whatever it was from that, and basically we found that the properties of the agarose are really not bad. It's not as good as probably the imported agarose, but we were getting there. And later on, of course, we made a product that was absolutely world class. But the only thing is, in nature, it was only available in small pockets and maybe a few kilograms of material. And so I knew that there's no way that you can have a commercial business without the raw material, and few kilograms and all is of no interest. Then I managed to shift this from Gujarat to Tamil Nadu. We had a field station there, and one of my colleagues, Dr. Ishwaran, he was able to grow this by the tons, and we developed the technology for actually cultivating this in the sea. And so suddenly we had a lot of feedstock, with us, and we said, "Oh, this is great. We must try and now make agarose in large quantities." Now, the way these typical compounds, these are known as phycocolloids, they're derived from the seaweed, and they are all thickening agents, gums. The way they are isolated from the seaweed is that you boil it in water, these seaweeds, okay, and the agarose or the agar, it tends to come into the solution, okay? And after that you separate out all the debris, and the problem is that you cannot make a concentrated solution, because these things at even 1 or 2% concentrations can suddenly become a hard gel, and so you're trying to do filtration and it's gone. I mean, you will not be able to process it further. Okay, so what people do is, to circumvent that, they make a very dilute solution, less than 1%. Okay, and typically these compounds, these phycocolloids, are readily dispersible in water at high temperature. Means if you go to around 80, 90, 100 degree centigrade, they will nicely dissolve or disperse, whatever you want to call it. Okay, but in the cold conditions, they will not dissolve. Okay, so they can only be dissolved under hot conditions. Okay, so what was developed not by us, this was very well known earlier, that they used to freeze this stuff. You know? So you literally convert it into ice, and you look at some of these giant factories which are taking this and making ice out of it. Okay, and then once it freezes and then you thaw it, the ice melts. Okay, but because the agaros are not cold water soluble, so those remain. So you drain out the water, and maybe you can repeat the process a couple of times, and you can get a very pure compound. And that's the way we initially made the agaros and carried out a lot of work with it. But it used to always trouble me that it's such an energy inefficient process. Can you imagine freezing so much of water, converting it into ice, and doing it maybe 2, 3 times to get a pure compound? You know, it just seemed like ripe for that. Is there any other way? You know, and so around 2001, I had actually initiated a project initially in MS University in Baroda to one of the professors there, and I had said that let us look at. It was just a fundamental research project. Okay, just let us look at the interaction of surfactants, with these kinds of molecules. You know? And I was not interested actually at that time in anything else. You know, this man wanted a project, and I thought that this could be an interesting project to give him. Now, later on, it turned out we could apply some of the findings that he was able to develop, into this extract. And what happened was that we found that the agarose, in the presence of this surfactant, Titan X 100, okay, this is surfactant. You can see it's basically a ethoxylate type of surfactant, okay, and the agarose just coagulated out from solution, okay, and so there was no need to freeze. So we could actually just separate it out. We just did a centrifugation and took out all the water and got a very compact solid. And then, of course, after that, carried out recrystallization of this compound, and finally developed some technologies to recycle the Triton X100. And so it became a very nice technology. What was very interesting, and why I'm talking about a win-win situation, none of that is win-win. That is basically a process innovation. Okay, but the win-win thing was that when we started looking at the structures of agaros, the ones which are the most costly, okay, what we found is that they have most of the standard phycocolloids. Some of these hydroxyl groups are in a sulfated form. Okay, so there is a side. This OH is actually OSO4, or OSO3 minus, and whereas this agaros and all, they were almost close to neutral. That is, there's no sulfate, or even if there is, it's negligible. And this Triton X100 worked with this kind of a phycocolloid with a very, very low sulfate content. That is the stuff that agarose is made of. So what happened was that the costliest product, okay, was the easiest to process, and the other ones, the cheap stuff, like the jello pudding type of agar, I mean, it didn't really work well by this methodology of coagulation. But the costliest one did. And so, and these, when I say costliest, these actually cost something like 50,000 rupees a kg. That's the kind of cost. And so it was a remarkable thing. In fact, subsequently, we could make very pure products, and it was compared to the best of agarose world over. Whether it is from Sigma or Merck, and all this work was done. It's been done by laboratories from all over the world. Including human DNA and the separations, and it was literally identical. What is important in our context is that we had a win-win situation, uh, like uh, uh, like Sharpless, that the highest, more concentrated solutions gave the best results. I was looking at this patent from Merck. I was familiar with this work. So when I was preparing this lecture for asymmetric synthesis, I dug out this patent of Merck, and it's quite clear to me that Merck actually did their work earlier than what Sharpless had done. But it's not that they did what Sharpless did. They did something very different, but they applied the cinchona alkaloids. So that he did, okay, and but he applied it in a totally different reaction where he did some substitution reactions, okay. But I think that maybe Sharpless was trying to prove the point that he had done something very original with the cinchona alkaloid, but that's not true, okay? Because the use of the cinchona alkaloid as a asymmetric catalyst has was done by Merck, and frankly, we know that Oswald and Bredig had done it in 1912. This is the cinchona alkaloid, okay, and I've shown you this before how they did the hydrocyanation of simple aldehydes and made chiral compounds. So in that sense, neither Merck nor Sharpless can claim credit for using cinchona alkaloid, but they can claim credit for applying it in different reactions. Okay, now here again, and this is where it becomes more and more important for engineers. And like one, as I told you, I mean that high concentrations actually gave a better product. What better thing for a chemical engineer to be able to be serve something like that on a platter? But there was something more. And I'll go back to Haber. That you remember that Haber was the first person who made an osmium catalyst, which lowered the activation energy for synthesis of ammonia, and he was therefore able to lower the temperature and get a better conversion after he had worked out the pressure temperature relationship of the equilibrium. And but then BASF could not proceed with osmium because, as we know, I mean, Bosch had said that osmium, if you collected all of the osmium in the world, it would not even amount to a ton of material at that time. And so they had to abandon that approach. And then, in a way, they rediscovered the ion catalyst, which initially Ramsay and Young had developed. So, I mean, this is great that this osmium-based chemistry and asymmetric synthesis was gave good results. But the fact of the matter is that it was only of limited interest because you required stoichiometric amounts of the osmium compound. Now, this company Upjohn had carried out various kinds of reactions with osmium tetroxide, but what Upjohn did was that they were able to. You start with osmium 8, okay, and after it does its hydroxylation job, as I told you, it gets converted into osmium 6 and it gives you the dihydroxylated product. Upjohn were not working on any asymmetric synthesis, and this was long before Sharpless started working on it. So this work was very well known long before, and then what they did was recognizing that osmium is in short supply. Uh, they were able to take an oxidizing agent, and over here they took morpholine. This morpholine with an N oxide. So there is an oxygen which is introduced on the nitrogen, okay, and so that's methyl morpholine N oxide, and they could actually convert back the osmium 6 into osmium 8. Okay, so what it meant is that now my oxidizing agent is N-morpholine oxide, and it is not osmium tetroxide because it is getting recycled. Finally, what I'm consuming is this. And that actually opened up the whole area of hydroxylation with osmium tetroxide, because you could just run this forever, this particular cycle. And many different compounds were produced. But at that time, as I said, the focus was really on not on asymmetric synthesis, but just on making simple dihydroxide. Now, then what Sharpless did, as I told you, Sharpless was really good, at latching on to prior art, the work of others, and then bringing in his own creativity, and a sense of purpose. So what he said is, oh, I've already done all this work with osmium tetroxide, asymmetric synthesis. So why don't I just now incorporate the work of Upjohn, and that's what he did. So into that asymmetric dihydroxylation scheme, he introduced this recycle of osmium tetroxide. Only thing is that Upjohn had done it with that N-methyl morpholine oxide, and whereas Sharpless, he was able to show that you can do the same thing with ferricyanide. So he could use ferricyanide and oxidize the osmium 6 to osmium 8 and generate ferrocyanide, okay, to the iron 2. And then, of course, there are simple ways of reoxidizing ferrocyanide to ferricyanide. Now, but look at the impact of this work. That, by doing this, Sharpless was able to carry out asymmetric synthesis with a substrate to catalyst ratio of 50,000 to 1. Already we have seen that Noyori was able to reach some figures of 10,000 to 1. And if that seemed like high, this was even higher, 50,000 to 1. And so what it meant is that the non-availability of osmium tetroxide was no longer a big issue, because this problem had been circumvented. You could keep on recycling the osmium 8. Okay, so that's what he did. And the interesting thing is that Sharpless also gives us a plot which I found quite interesting. And he talked about his passion for these kinds of elements. That there was a time when, long back, okay, when selenium dioxide used to be used as an oxidizing agent. Have any of you heard of the use of selenium dioxide as an oxidizing agent? Anyone is aware? It's a great reagent. Like, for example, you can convert a methyl into an aldehyde, and methyl is otherwise so unreactive. So there was a lot of interest in selenium dioxide as an oxidizing agent. But after Sharpless invented his allylic alcohol-based epoxidation, quite a bit of the interest shifted to this, at least in terms of publication. And then, the work on osmium tetroxide was very important after the work of Upjohn, over here. Okay, and then the work on titanium-based epoxidation became very important. And after Sharpless was able to marry, the ideas of Upjohn with his own work on asymmetric synthesis, he ended up really doing something quite magical, and so the entire area of osmium tetroxide based asymmetric dihydroxylation really shot through the roof, and it became an extremely powerful tool in the hands of industry. That industries today can actually do asymmetric synthesis and they actually practice it with the work of Sharpless. I thought that it is very important that I also tell you a little more about in a sense, the continuation of that work, which led to the Nobel Prize last year. You know, and I read out to you, or I played a little bit of the video of Benjamin List last time, and I will show you a little more about what exactly he did. You know, it's important that we understand that. Okay, and I and we need to keep this in mind also, that in a way, I will say Benjamin List really rediscovered work which was published in a patent where they used this compound proline. Okay, so proline is just an organic compound. It's an amino acid, of course, but it's a simple organic compound. You can just look at it that way. Also, note that all these amino acids, they have an amine means a basic character as well as an acidic character. Okay? This is quite important. And actually, what these people had done was that they were able to do aldol type of reactions using this particular thing as the catalyst. Okay, and really ended up with exceptional results. Chiral molecules produced with very high yield. And I kept asking myself that how on earth did Benjamin List and others really, why did they become so famous? Because they were just working on things which people had already done before. And later on, I started studying Benjamin List's uh, patents and papers and all, and I realized that actually Benjamin List does not really have any patent on the use of proline as such to make an asymmetric chiral product, because that's already known. Okay? But subsequently, Benjamin List did some extraordinary work, which I'll tell you about. I also realized that List was very prolific in the way he expanded the scope of his whatever work he had done, and that must be one of the reasons why he got the Nobel Prize. He extended the scope, and actually the thing where he really made a huge contribution. Okay? And he talks about it, but I thought from the beginning itself, I'll tell you about it. Okay, that he was able to move into what I will say, like mimicking enzymes in a way that there are certain pockets in enzymes where you could have, for example, extremely high acidity without exposing the rest of the environment to a high acid. So it's like a confinement. Okay, and so these kinds of things of confined pockets, where action takes place, okay, is it completely opened up the area. And I was just looking at how important this whole area of confinement is, which he talks about. Okay, Benjamin List. So I have put down over here some of the things which I felt were possibly the things that Benjamin List can claim credit for. I also felt that many times, these people try to impress you with a lot of very fundamental research. But the truth of the matter is that it will not stand in the court of law when it comes to patents. That people will say, yeah, okay, all that is fine, but you're still infringing on the prior art of these people. So what I'll do is, just for a few minutes, okay, I will play to you a portion of Benjamin List's Nobel lecture.
I became fascinated with this idea of creating artificial biocatalysts that would engage in the catalysis of non-natural reactions. And at that time, in the mid to late 90s, one approach appeared to be particularly attractive to me, and that was catalytic antibodies. And I was very fortunate to be able to move to the Scripps Research Institute and to work with Professor Lerner at Barbas on the utilization of aldolase catalytic antibodies. They had just discovered an aldolase catalytic antibody that would catalyze with high efficiency and also very high selectivity aldol reactions. And I was excited to work in this field all of a sudden, and I used this antibody to do large-scale experiments, gram-scale experiments. I also used this antibody in the synthesis of natural products, actually. But the main thing I was interested in was to understand how this antibody actually does its catalysis. And fortunately, at the time, a crystal structure of this antibody was available. And what that revealed was that in the active site of the antibody, you have on the one hand an amino group derived of lysine residue, and then a water molecule that bridges this amino group to a tyrosine hydroxy group. And for me, this immediately suggested that perhaps the mechanism is in fact a bifunctional mechanism where you have an amino group that, assisted by the acid group, engages in the formation of an iminium ion from a ketone precursor. And this iminium ion formation is actually quite important. It not only lowers the LUMO energy of this system, but it also drastically increases the alpha CH bond acidity. This has been estimated by Bill Jenks already in the 60s. I think this was done in the context of work on the mechanism of class 1 aldolases. And so now the conjugate base of this acid co-catalyst can now extract the proton to generate an enamine intermediate. So as you can see, this is basically a strategy that biology has developed or evolved, one should say, to enable carbanion equivalent formation under physiological conditions in water without the availability, of course, of stoichiometric organometallic bases. So this enamine then can engage in a direct CC bond formation with an aldehyde, for example, assisted by the Brunson acid co-catalyst, which protonates the nascent oxyanion in the transition state to generate the iminium ion of the aldol product. And then hydrolysis occurs, once again assisted by the conjugate base of this acid co-catalyst to generate the aldol product and to regenerate this bifunctional enzyme, as I like to call this. So that was the thinking that I developed. And this, in fact, encouraged me much later in January of 1999, when I became an assistant professor and when I was thinking about my independent work, to think again along the lines of Oswald. Why is it not possible to design organic, simple molecules that have all the machinery that is needed to catalyze such an aldol reaction? And I realized all that is needed is an amino group and an acid group, right? And so with that, I started to designing potential small molecule catalysts when I remembered, of course, there already is a catalyst like this. There is an amino acid, in fact, that catalyzes aldol reactions. And that is, of course, proline in the famous Hyers-Parrish Edersauer-Wiechert reaction that was very well known to me, of course, since my undergraduate studies in Berlin. And in this process, proline catalyzes an intramolecular aldol reaction to give these bicyclic ketones, which the idea had been could be useful intermediates in developing industrial routes to steroids. This never became a reality, in fact, because steroids are made from natural products and the supply of these natural products was sufficient. However, it was still an important discovery, somewhat an underappreciated discovery. People were slightly confused, I think, about the mechanism. But in that moment, I realized actually what is probably happening is that proline is just the essence of an aldolase enzyme. It has all that is needed. It has an amino group, actually a privileged amino group for iminium ion and enamine formation, and it has a carboxylic acid that can act as the co-catalyst, the Brunson acid-base co-catalyst. And so this is the hypothesis I developed as a fresh assistant professor at Scripps. I hoped that proline would function like a microaldolase, as I called it, by converting first the ketone assisted by the Brunson acid into the corresponding iminium ion. And then the carboxylate would deprotonate this iminium ion to form the corresponding enamine. And the enamine, in turn, would then be able to react with an aldehyde to form the carbon-carbon bond, where the proton is transferred in the transition state onto the oxygen, the oxyanion of the aldehyde that is being formed. And then the iminium ion, the last step, would be hydrolyzed with water to form the aldol product and regenerate the proline catalyst. This was the hypothesis I developed. It's kind of actually one of the few catalytic cycles that I designed, and that then, when I did the experiment, actually worked. And this is also what happened in this case. I was very excited when I discovered that indeed proline also catalyzes intermolecular aldol reactions of ketones with aldehydes to give very valuable aldol products in really excellent yields and state-of-the-art enantioselectivity also. And I think it is important to mention in this context that the so-called direct asymmetric aldol reaction at the time was considered one of the biggest challenge of asymmetric catalysis, and there had been only one solution to this problem, and that was a sophisticated lanthanum-based, fancy transition matter-based catalyst that was developed in the group of Shibazaki in Japan. And all of a sudden, it turns out there is now an edible, non-toxic, readily available catalyst that gives the same kind of reactivity with state-of-the-art selectivity. For me, this was a big breakthrough. I was very excited at the time, and we were really happy to see that the reaction was also not limited to one aldehyde, but in fact, we could convert several other aldehydes as well to give the desired aldol products, in some cases really with enormous enantioselectivity. In fact, we have just submitted a manuscript to Organic Synthesis, which allows in a reproducible fashion for hopefully all undergraduate students in the world to do these experiments on a gram scale. So that was quite exciting. But already during those studies, I realized there's probably more in this kind of chemistry. Proline is not just a microaldolase. Proline is a catalyst that can convert carbonyl compounds catalytically without requiring a stoichiometric reagent or auxiliary into the corresponding enolate equivalents, right? And so this then led to what we have called, MacMillan also, my co-laureate, a wonderful colleague, by the way, what we have called a generic activation mode for organocatalysis. So proline actually has this generic activation mode that we have called enamine catalysis. It converts carbonyl compounds into the corresponding enamine. And now this enamine, of course, should not only be able to react with aldehydes in aldol reactions, but it should in principle be capable of reacting with any type of electrophile. So in principle, it should be able to react with an imine, it should be able to react with the Michael acceptor, even alkyl halides, how about oxygen, nitrosobenzene, dialkyl azo-dicarboxylates, and all of these wonderful electrophiles in principle should, according to this catalytic cycle design, engage in such transformations, CX bond formations. And so this was then the program of the following years. And indeed, I could show with my slowly growing group that enamine catalysis is actually a solid concept, and we discovered a number of different reactions. I should also emphasize that in these early days, we initiated a collaboration with Professor Ken Hauck at UCLA, and that was a very fruitful collaboration in which he provided theoretical computations on the mechanism of our reaction, while we in the meantime did kinetic studies and other mechanistic work. And all of that boiled down to what is now called the Hauck-List transition state of the aldol reaction. And I said this before, who knows the final truth of this mechanism? In any case, this model has a very powerful predictive character, and all of the reactions I will be discussing with you today could have, or indeed have been predicted on the basis of this transition state. For example, our proline-catalyzed aldol reaction, the stereochemistry of this is well explained with the Hauck-List transition state, and so is the stereochemistry of these other two intramolecular aldol reactions we discovered, the enol exoaldolization of dialdehydes to give cyclic aldols, and also the first catalytic asymmetric transannular aldolization to give these natural product precursors that we indeed have used in very efficient natural product synthesis. But in addition to carbonyl compounds, as I said before, you can also use other electrophiles. For example, we were excited to find the very first example of a catalytic asymmetric alpha alkylation of an aldehyde. And that is a novel type of reaction because it's not an addition reaction, but it's a nucleophilic substitution reaction. And it also gave cyclic products in excellent enantioselectivities. And already back in 2000, we had shown that Mannich reactions, actually the first catalytic asymmetric three-component Mannich reaction of a ketone, an aldehyde, and an amine can be catalyzed with proline once again. And we made these ketones here, but also a number of other products based on this very general and very powerful and highly useful Mannich reaction, for example. products in really excellent in anti-selectivity. And last but not least, I would also like to emphasize one example where not a CC bond is generated, but in fact a CN bond in the formation of these alpha hydroxidoaldehydes, which are great precursors to making alpha amino acids. Actually, we found that this reaction can once again be catalyzed by proline with very good selectivities and also very good yields. I should at this point again emphasize that this was then became more and more a field, and many different groups have started to engage in studying enamine catalysis and developing novel reactivity and novel reactions. And this is just a small fraction of all the beautiful transformations that were discovered during those days. Some people called them the gold rush in organocatalysis. But I would like to still highlight one additional reaction that I think is kind of timely, and that was a proline-catalyzed intermolecular aldol reaction of two different aldehydes. This is actually a development that goes back to work done in my laboratory, but that was later then advanced by my co-laureate, Professor David MacMillan. And the group at DSM, actually in the Netherlands, found that this cross-aldolization of two different aldehydes gives an aldol product that can be readily converted into darunavir. And darunavir, as the name suggests, is an antiviral agent. However, enamine catalysis, of course, is not just the whole story. In fact, this is just one example of a generic activation mode that was developed in the context of organocatalysis. Many other generic activation modes have been developed in the meantime. For example, of course, immunoion catalysis. This is Professor MacMillan's main area of research in the early days of organocatalysis, and he has used this very elegantly in cyclo additions and in conjugate additions. But as I said, it also forms the basis of enamine catalysis by this acidification of the alpha CH bonds. But there are other also very powerful generic activation modes. Consider, for example, anion binding catalysis, where hydrogen bonding catalyst binds to anions to generate supramolecular chiral anions that then can engage in nucleophilic addition reactions, for example, with very high anti-selectivity. Very fruitful concept that has led to numerous very important publications in the field of organocatalysis. Acyl ammonium ion catalysis is yet another generic activation of organocatalysis, where acyl groups are transferred from one substrate to another substrate, and it's also a very powerful organocatalysis strategy, widely used all over the world. Carbene catalysis, a very unusual mode of reactivity that is actually quite old, but that also has been massively advanced during the last 20 years, where aldehydes are so-called upoled. So the aldehyde, which is normally is an electrophile, is converted into a nucleophile. And this unusual reactivity can be utilized in many different, very elegant and important transformations. And last but not least, the only additional generic activation mode I would like to show here today is, of course, Brunzett acid catalysis, because of its very high importance that it has gained in recent years. And I will say more to that in just a minute. Suffice to say that this is, again, just a small collection of generic activation modes that came out of organocatalysis. There are many, many more. And all of these generic activation modes have led to numerous different transformations, some of which are even applied on a technical scale in the synthesis of pharmaceuticals and scent molecules, for example. Now, at this point, it's also helpful, to organize organocatalysis. And I have found a very useful way in doing so. And this goes along the definition that I prefer, and that is organocatalysis is the catalysis with small organic molecules, where a metal, of course, is not part of the activation principle, and that function by donating or removing electrons or protons. And that automatically creates four sub-areas of organocatalysis: Brunzett acid catalysis, Brunzett base catalysis, Lewis base catalysis, and Lewis acid catalysis. And these are the catalysts that either donate or remove protons or donate or remove electrons. And this actually brings some nice organization into the field of organocatalysis, and it also brings to the surface gaps where actually nobody works on, I found. And my lab, we became particularly interested in the utilization of Lewis acid catalysts. And this is what we're doing actually right now. We're really fascinated with the power and potential of acid catalysis because of its universality. Because after all that acids need for catalysis is electron density. And this is pretty much what chemistry is all about, electron density, right? And so we realized that actually possibly the vast majority of all catalyzable reactions can be catalyzed with acids. And so over the years then we have advanced our little proline molecule, which is a Brunstad acid, don't forget that it has a pKa of around 20, to much more acidic and also more complicated acids that in the meantime have reached acidities in the pKa scale in acetonitrile of below 2 units. So that means these rival the acidity of superacids and triflurid, for example. But in addition to this, they have a unique feature, and we call this confinement. So around this is acid functionality, confined pocket evolves with this catalyst design, simulating somewhat how enzymes catalyze their reactions. And with this special combination of high acidity and confinement, a number of unique transformations have been realized in recent years, and I would like to highlight 6 of them to you. Number 1 is a cross-aldol reaction or a Mukayama-aldol reaction of the acetaldehyde-derived enol-silane with yet another aldehyde to give the corresponding aldol product an excellent enantioselectivity. Looks kind of simple, but in fact it's an amazing transformation because previously this combination of an enol-silane of acetaldehyde with yet another aldehyde would just lead to polymerization. Because as surely you have noticed, both the starting material and the product have an identical functional group, an alpha unbranched aliphatic aldehyde. And yet, with the magic of these confined acids, the product is simply not a substrate anymore for the catalyst. It ends after a single aldolization to make these very important aldol products. We can also catalyze other Mukayama-aldol reactions. For example, Mukayama-aldol reactions of ketene acetals with ketones. And that was a challenging reaction at the time. And not only can we do this, but we can do this with parts per million catalyst loading. In fact, in this paper, we describe one example where we use below 1 part per million as the catalyst, which I think is the lowest catalyst loading that has ever been used in any catalytic asymmetric carbon compound forming reaction. There might be enzymes that are as good as this, but I'm at least not aware of. We can catalyze Diels-Alder reactions, but not just the usual ones, but very challenging ones where we combine unreactive dienes with unreactive dienophiles and make these cyclohexene products for the first time catalytically and with high enantioselectivity. We can also catalyze heterodiels-Alder reactions of now all types of dienes with all types of aldehydes to give these useful products here. And it's kind of remarkable to realize that such a transformation was unprecedented even with achiral catalysts. So it's actually even unusual reactivity that is enabled by these confined strong acids. We can also now, with this high reactivity, finally activate olefins for asymmetric catalysis. This has been the domain of transition metal catalysis, but now actually organocatalysis for the first time can also enable the activation of simple olefins, in this case to form the corresponding carbon cations, which then engage in the nucleophilic addition to form tetrahydrofurans. And very last but not least, I would like to share one recent discovery in my group. We have found that IDPi catalysts can actually mediate the addition of TMS cyanide to 2-butanol. Looks simple, but it turns out this product of this silyl cyanation reaction is a valuable intermediate in the synthesis of 2 pharmaceuticals. And it also turns out that all previously developed chiral catalysts for silyl cyanations and hydrocyanation reactions, and these include very sophisticated transition metal complexes, even more sophisticated organocatalysts, and also very advanced enzymes and even engineered enzymes, and none of these catalysts was able to deliver this product with greater than 95 to 5 ER. So this is actually a milestone, I would argue, in the history of organocatalysis. We're very excited about this because finally this idea of Oswald that chemists are now able to design organic molecules that enable enzyme-like selectivity and reactivity seems to become.
Could you hear it clearly?
Yes, sir.
Huh? Okay. Now I don't expect you that you'll understand all of the reactions and things like that. Okay, but there are a few messages which I'm trying to get across. Starting from something extremely simple, okay, how an entire field develops. This is something so remarkable. And this is where you can have tremendous opportunity when you've got large, let's say, skilled manpower. And if you can organize people well, that they can end up exploring so many different kinds of reactions. And and you can see, even though his initial work is not novel in the sense that proline is already been reported. Okay, so there was prior art. Let's not kid ourselves on that. But the subsequent works, and especially the work that he did with where he developed these very strongly acidic confined pockets, I think that that part of the work and its application to organocatalysis is extremely important. What there are two people who got the Nobel Prize, as I had mentioned to you, and as you are yourself aware. The other one was David MacMillan. MacMillan has, in some ways, you see, if you don't know exactly what's if you don't go into the details of it, it will look quite similar between the work which, let's say, Benjamin List did and what he has done. Okay, but that's not true. And in fact, I checked out with my former roommate, John, asked him whether he had ever interacted with Professor MacMillan. And I also asked him that is really organocatalysis being practiced by industries? And he confirmed to me that organocatalysis is big. Okay? But I think Macmillan's current work in photoredox catalysis is bigger. Okay, and so I just thought I will play to you that part of Macmillan's work where he talks about photoredox catalysis. And it's interesting because when almost everything looks saturated and there's not much to do, and that someone can come up with an extremely bright idea, which is what one of Macmillan's students actually came up with. Okay, and he talks about that. And the second is that the initial intermediate which is formed prior to forming enamine, which is the iminium ion. Okay, that is what Macmillan exploited more than what Benjamin List did. And List, of course, mentions about that Macmillan was then able to do a wide variety of reactions, with the iminium ion rather than with the enamine. They all look very, very similar. It's only a subtle balance, but obviously Macmillan had great success in doing that. So what I'll do is I'll only play, as I said, only that part of Macmillan's lecture, which is relevant to photoredox catalysis.
The next type of reactivity we became interested in was organic radicals. So this is Moses Goldberg, who's the person who discovered radicals in 1901. There's this really wonderful statement in his manuscript that says, "This work will be continued, and I wish to reserve the field for myself." Well, clearly that did not happen. All of the chemistry world started to use radicals. And the reason was because, as the name suggests, radicals allow you to do radical things. They allow you to achieve radical reactivity. And so we became really interested in could you merge this with organocatalysis. So this was actually work that was conceived of and executed on by a really fantastic graduate student in my group, Barry. What Teresa did was she said, I should be able to make the same enamine, but instead of using these enamines to do chemistry, what if we actually plugged an electron out to change its reactivity now that it's a radical? This radical should allow you to do many, many different new types of chemical reactions. And that turned out to be exactly the case. We published many new types of processes using what's called this somocatalysis. But this actually became a stepping stone for us to think about, could we actually take radicals and organocatalysis and make it even more sustainable in terms of how we'd actually perform these transformations? In this context, we became really excited about the fact of being able to sort of harness visible light with organocatalysis. Now, harnessing visible light is something that inorganic chemists have been working on for almost 3 decades. And the idea here was to try and harness the light that comes from the sun and use that as energy to power the planet. We became interested in the idea of putting
take that knowledge that they had developed and then transport it into the organic world. And once it was in the organic world, start to think we're doing a thing called photoredox catalysis. This would allow us to make new bonds. This would allow us to perform new types of transformations that could have a whole variety of different applications. Now, it turns out this was actually work that was performed in collaboration with a wonderful postdoc in my group by the name of David Savage. This is basically what we were attempting to show in this slide. We're taking light bulbs, we're taking organocatalysis, and then the right moment we simply switch on the light, we switch on the blue LED, and new chemistry starts to happen. Now, what's really exciting about photoredox is that it became a field in and of itself. It actually became a field as large as organocatalysis, and that's something that we're very much proud to be a part of. Now, in terms of thinking about this, the part that's really exciting is we've been really lucky as a group to be involved with organocatalysis. And we've also been really lucky to be involved with this field of photoredox catalysis. It's been really exciting to see that organocatalysis effectively created this bridge, at least in our lab, into photoredox catalysis. In fact, if you think about it, it really was a catalyst that allowed photoredox catalysis field to come together, again, at least in our lab. Okay, so at this point, another question that a lot of people ask me is, what about applications of organocatalysis? And I'm going to show you just a few. The first one is in the area of fragrances, perfumes. It turns out perfumes are used on an enormous scale across the world every single day. In Firmenich, this company that's in Switzerland, Geneva, are very successful at performing and producing many of these different perfumes. And one of the ones which is actually shown here is produced by combining organocatalysis with photoredox. This actually makes the lily of the valley. Turns out Firmenich, also in northern India, made 300 metric tons of this beautiful rose-smelling perfume, also using organocatalysis. Okay, so that's perfumes. What other areas can you use organocatalysis for? Well, you can actually use it in terms of materials and actually for the recyclable plastic economy. This is some very important work that's being conducted by Bob Wayman and James Hedley. And many of you probably know that plastics are polluting our oceans. What Bob and James are doing is they're using organocatalysis to effectively break down polymers back down to monomers, which can then be used again to remake polymers, making polymers and plastics completely recyclable and completely sustainable, which is obviously extremely important. But the area in which organocatalysis is probably most heavily used is that towards making medicine or developing medicine. I'm just going to show you one example. This is tetroxide-mediated. It's actually used to treat chronic migraines. This particular molecule, this particular medicine, is actually made, and it's made using organocatalysis. And in fact, it uses the aminium catalysis I talked about at the beginning of my talk to make one of the meta remedies reference to the other.
I've covered the part which is most significant of his work. I don't know whether you could follow it, but you know, it's interesting that he could, when everybody was working on the enamine, okay, that they thought of making the radical of enamine, and that completely opened up a new area, and the versatility was enormous because of that, and that's what really the photoredox catalysis was used for. So this is again something when everything looks as if you are pretty much exhausted in terms of ideas. Always ask yourself, and you'll have to go to radically new ways of asking questions, okay? And never hesitate. Never hesitate to ask very, very stupid questions, okay? And something very interesting might come out of that. This area of photoredox catalysis and generally catalyzing organic reactions with light is not a new concept. In fact, many of the things one does, many of the bromination reactions, etc., are actually catalyzed by light. I think the new part is that they were able to use it in a very clever way and in a most appropriate system. I think that's again very important. If you say, I'm also doing photocatalysis, yeah, you are, okay, but it could be not in necessarily the most exciting area. So with that, we come to the end of organocatalysis. Now, I'm not going to read out all of this, but I want you to read and also to maybe incorporate your own thoughts of what came to your mind. But I just thought I'll put down what were some of the important lessons that one can learn from these Nobel lectures of all these great people who were covered, and also people who didn't get the Nobel Prize, like Kagan. A few things which were very apparent to me. Okay, one was that they spotted a good idea long before anybody else did. That was very important. They drew on already existing prior art, and then they adapted it for their own purpose, which was very important. They were quite curious and testing out minor changes like changing over from an acetate to a halide or switching over from a rhodium to ruthenium just out of curiosity. Okay, and or making a radical of enamine, and at that time they didn't really know what's going to happen. Okay, but something very interesting happened. We've learned from someone like Knowles what doggedness in going from something like a 1% enantiomeric excess to 100% almost, and this is again very interesting. Many of these people had excellent industry academia collaborations, so I'm sure a lot of the focus of their work, especially Knowles with his L-DOPA, that would have spurred him on, that there is a clear sense of purpose behind his work. It was extremely important. Knowles, while he focused on one product and tried to improve it to the maximum extent he could, but List and MacMillan and Noyori were people who really diversified the area. That's why they got the Nobel Prize. It was not because they did something extremely original to start with. Let's not kid ourselves. It was already there. Proline was used as a catalyst. So I don't think that they can claim credit for that. But the way they expanded and made the whole area useful, and the fact they're doing these things with almost like edible catalysts, you can imagine what a huge change. And also, I think in many cases, people were quite lucky. So luck was on their side, no question about it. And also, you've seen their articulation skills are very good. Sharpless was excellent at connecting the dots, and took things from the literature, and there were scattered pieces of things, and he just connected the dots, especially the way he integrated the Upjohn process with his own process. So these are some of the lessons, and also the use of natural chiral pools, which we saw both Kagan and Sharpless do, where both of them use tartaric acid rather than synthetic, and same with proline available from nature. So these were the kinds of things which you can learn as common lessons.